Today we have a log problem. We have solve for x, log base 3 of x plus log base 3 of x plus 5 equal to 1. So there's a couple key important pieces of information that you need to be aware of here. First, you got to know the properties. Because we have the same base and we have addition, there are some properties that we can use to put this in a more favorable position where it'll allow us to actually solve for x. Because right now, like, our hands are kind of tied the way it's written right now. But if we know that this is addition and we have the same base, we can use the product rule. The product rule says that I can replace, let me write that. I could rewrite this as log base 3 of x times x plus 5. So since it's plus, I could write this as x times x plus 5. That is the product rule. If it was minus, you'd have the quotient rule. It'd be x over x plus 5. But since it's plus, we can just rewrite this as x times x plus 5 equal to 1. So that's first key property. The next is just understanding what log, the relationship between logs are. Like when you have the base and it's equal to something and that term on the inside, like what does this actually translate to? How do we actually change this into a way that we could solve for x? Well, what we need to understand now is if I have log base a of x equal to b, the relationship here is that a to the b is equal to x. So a to this term, so the base to the term that it's equal to, the number that it's equal to, a to the b, is equal to what's on the inside of the log. In our example then, that's going to be 3 to the first is equal to x times x plus 5. We used two properties to just make this a little bit more compact, and look, we no longer have log base 3 because we understood the property of if I have log base a of x equal to b, that is a to the b equal to x. And you could do that for any scenario with logs as long as you have the right pieces in place. But now we can now solve. Look, we have 3 to the first is 3, x times x times 5, x times x is x squared, x times 5 is 5x. And now I want to get set equal to 0, so I'm going to subtract 3 from both sides. I get x squared plus 5x minus 3 equal to 0. Unfortunately, we have a situation now where we can't factor this, so I have to either complete the square or use quadratic formula. I'm just going to go the route of using quadratic formula. And the quadratic formula is negative b plus minus the square root of b squared minus 4ac all over 2a. My a term is 1, my b term is 5, and my c term is negative 3. So let's just put everything into place. So negative b, negative 5, plus and minus the square root of 5 squared minus 4 times the a value of 1 times the c value of negative 3 all over 2 times 1. Let's see how this breaks down. On the left side at negative 5, because that was the opposite of b. b was positive 5, so it becomes negative 5. Plus and minus the square root of b squared is 25. Minus 4 times 1 times negative 3. 1 times negative 3 is negative 3. Negative 3 times negative 4 is positive 12. Over 2 times 1 is 2. (25 plus 12 is 37. I'm going to have negative 5 plus and minus the square root of 37 all over 2. And it looks like we are done here. I don't see any other moves. 37 is prime. I'm not seeing anything else. No other moves to make. So there is our solution to this problem. Going back to the original form, like you would never, if you're new to figuring out what logs are, like looking at this, you would never guess that this would be our solution, right? Like it just looks so crazy that we were able to condense this down to this term of just a single log, x times x plus 5, because we have addition, so we use the product rule. And then we were even able to take a step further, just understanding the relationship of logs. And then boom, we're into quadratic formula. and we're good from there. So fun question. Logs can get pretty crazy at times. Pretty crazy. And that one was pretty moderate, I would say. Pretty moderate. Nothing too tricky, nothing too hard to see in terms of what we would do next. So pretty straightforward log question there.